Previously, we were tasked to count who put how much cereal into a cereal silo. However, we could not rule out evil demons from tricking us. Demons can appear in the forms of villagers that try to convince us they put in more cereal into the silo than they did. Demons can cause forgetfulness or even implant false memories. Note that the demons we are interested in can only influence the map, not the territory. There is an actual number of sheaves of wheat that were put into the silos, but our map does not capture this reliably. This is of stark contrast to the rationalists, where the territory is seen as unreliable. Rationalists try to eliminate territory demons by reducing the territory to an ideal mathematical map through reason alone, so they don't have to rely on their senses of the territory anymore. We solved our problem by building a grain accounting machine that can detect the amount of grain it is given, can store that amount together with the face of the owner, and then retrieve the cereal when the owner requests it. This shifted the truth away from our map to the territory. However, during the construction of the machine, new demons can crop up. How do we eliminate these remaining demons? Chapter 3. Silly Solutions. Maybe we can create a machine that creates a grain accounting machine. That way, the construction of the machine happens outside of our mind. The demon chuckles. The demon, can still trick us when we construct this larger machine. Instead, let's build a grain accounting machine that can also build itself. In this way, one can run the machine as many times as one likes and have the copies build as many copies of themselves, and so on. Let's call it the Quinian grain accounting machine. But wouldn't building such a machine be arguably more complex and leave more places for demons to trick us than merely building a correct grain accounting machine? Unfortunately, it is. Engineers deal with this relentlessly. They try to create machines by mashing keys on a keyboard, and of course mental demons trick them constantly during their work. The engineers affectionately call these demons bugs. One of the ways engineers tackle them is through separation of concerns. The complexity of possible demons is reduced by first building small submachines and verify their demon freeness before building bigger machines from those submachines. But first, how do we even build these small submachines, let alone verify their correctness? Chapter 4. Building Machines. A simple class of machines you can build are deterministic finite automata that take a finite binary sequence of inputs and outputs either yes or no. Each deterministic finite automata has an initial state, indicated by an incoming arrow pointing to it. If the empty sequence should output yes, this state is also a final state. This is indicated by having two circles around that state. If the first letter of the sequence is a 0, we will follow the outgoing 0 arrow to the next state. If the next letter of the sequence is a 1, we will follow the outgoing 1 arrow, and so on. Our input sequence contains one more 1 and one more 0. This machine ends in a state without double circles, thus the output of the machine is no. Let's try this again for the first possible binary input sequences. The empty sequence will output yes. The sequence starting with a 0 will output yes. This sequence with a 1 will output no, and so on. Looking at the results, this machine seems to output yes if every 1 is preceded by 2 zeros in the binary sequence and no otherwise. Here is another machine. Can you tell what it does? No? Let's try the first few possible binary sequences as an input. Note that some sequences that start with a 0 were skipped. This is because the only sequence starting with a 0 that is accepted is, well, 0. If we only look at the accepted input sequences, we see that it contains all binary numbers which are divisible by 3 in binary. Wow! If you're lucky enough to not know what a binary number divisible by 3 is, I can tell you that this machine is exactly what a binary number divisible by 3 is. The machine outputs yes when typing in 110, therefore 110 is a binary integer divisible by 3. The machine asserts that 110 is a binary integer number divisible by 3. If, on the other hand, you are unlucky enough to have some preconceived notions of what a binary number divisible by 3 should be, you now need to judge whether your map of the territory corresponds to that of the machine. Your own preconceived notions have created a potential bug for you. The daemon can trick you into believing that these are equal, but you are not sure. Can you resolve this? To add some foreshadowing of what's to come, we will need a machine that decides whether your notion of a binary number divisible by 3 is equal to the notion of the aforementioned machine. Let's call this the Extensional Machine. Anyways, back to deterministic finite automata. We just created a way for machines to have a map. Our deterministic finite automata only care about whether a binary sequence is in their map or not. This can of course be extended to maps over any sequences over a limited alphabet. For example, this is a machine that checks whether a given sequence contains at least one papaya. For example, the sequence papaya contains papaya. Traditionally, we use the symbol sigma to denote an alphabet and sigma star for a sequence of it. A formal map is now a function from sequences to yes or no. Further, the problem of creating a machine for a given map is called the decision problem. It is important to note here that by construction, the finite state automata guarantees that it will output either yes or no. It leaves no mystery. Let's have a quick interlude for the inclined. Cantor showed that sequences of any alphabet are the same size. For us, this means that the choice of an alphabet sigma does not significantly affect what maps one can create. When he found this out, he thought a daemon played a trick on him. Let's have a look. Every alphabet you can think of has a canonical order, including the sequences over Latin characters and the binary sequences that we just studied. The 0th element is the empty sequence. Then we list the sequences, sorted first by their length and then by their symbols. The first element contains the Latin sequence A and the binary sequence 0. The second element contains the Latin sequence B and the binary sequence 1. The third element contains the Latin sequence C and the binary sequence 00, and so on. For example, the sequence papaya in the Latin characters appears at the 190,841,535th position. There is a one-to-one correspondence between Latin sequences and binary sequences. In this way, every decision problem over sigma can be reduced to a problem over the binary sequences after finding its canonical order. This can be done using a machine. As a challenge, find the canonical binary sequence of my name, Kevin, using a machine. So far we have created machines that decide whether or not a given binary sequence has each one preceded by 2 zeros, that decide whether a given binary sequence is a binary number divisible by 3, or that decide whether a given Latin sequence contains papaya. This is all fine and good, but can we get a more useful, practical machine? The ancient Greeks have created the famous Antikythera mechanism, which can decide whether or not a given day has a solar eclipse. One can set a day, for example, the 25th of November 2030, and the machine will output yes, as that day will have a solar eclipse. But why is the daemon sitting so comfortably? Isn't he scared that we're building more and more powerful machines that eliminate reliance on our map? The daemon has realized that we have preconceived notions of a solar eclipse and has sneakily placed a bug in the mechanism. We have not accounted for the Sun losing significant mass in the next 5.5 billion years, which will change Earth's orbit completely. Can we ever escape the daemon? To find out, please subscribe so you don't miss it, and like the video because it helps the algorithm. Thank you.